Welcome back to ECE 320A. We are now in Unit 7, which puts us in Chapter 13, and the first part of Chapter 13 that you need to be reading is indicated here, and homework number 7 is at the end of Unit 7, and we also have exam number 3 coming up after Unit number 8. What we want to do in this first part of Chapter 13 is look at starting or actually immediately going into an S-domain circuit and performing our circuit analysis in the frequency domain, and then at the final step or in the final stage take it into the time domain if we need a time domain answer. Which means that now what we want to do in this lecture or in this video is to actually motivate that particular concept. And that's the concept of transformed circuit elements, or looking at solving circuits in the S domain or in the frequency domain directly. Here's a motivation. Suppose that you're presented the following circuit. It's an RLC circuit, and one might want to know, how do you find the voltage across resistor R sub 2 on the right-hand side? And how do you find that in the time domain? The way that we've been doing it is, one way is to possibly write two integral differential equations. You could write two mesh equations, you could write nodal equations. Why do I want to write two? Well, I have two energy storage devices, and that means that I'm going to have a second order system to deal with, or two first order coupled differential equations that I need to then be examining or working with. And in the last chapter we found those equations in the time domain, and then we put those into the frequency domain by Laplace transforming those differential equations. And what we want to do now is actually avoid that initial step of writing the equations in the time domain. What we want to do is immediately convert a circuit like this into an S-domain equivalent circuit and analyze that in the frequency domain directly, and then we bypass this requirement that we have to write differential equations. Now we'll be able to write algebraic equations dealing with generalized impedance values, and those impedance values now will be associated with the inductors and the capacitors, and they will have S's, this complex frequency variable S, which is arising from the Laplace transform, as a part of that expression, or as a part of putting this particular circuit into the S domain. If we had to do it the other way, we would write two integral differential equations, and if one of those equations involves the current, for example, the current in the second mesh, if we had some mesh analysis and maybe we say here's I sub 1 of t, here's I sub 2 of t, if we could now find I sub 2 of t as a function of time, then we could immediately write down the voltage across that second resistor, since R sub 2 just scales that second mesh current I sub 2 by whatever R sub 2's value, numerical value, happens to be. And that really means that we're solving this coupled set of differential equations. And like I said, we could write the differential equations and then go into the frequency domain. What I want to do now is show you how we can actually write down by inspection. When we start with this particular circuit, we can actually immediately write down an equivalent circuit in the S domain, in the frequency domain, that is given as follows. And here we'll develop how this can actually happen in a minute, but what I want to do is just show you that it looks like structurally what we had before. It's just that now we have a couple of different pieces there, some voltage sources that maybe we didn't expect. Why are we seeing these voltage sources? And what you might take note of is in fact the expressions associated with those voltage sources. Those expressions actually contain initial conditions on the energy storage elements. We have an energy storage element here in the capacitor, and that capacitor's initial voltage is making up the expression for the voltage source there. And here we have the inductor current, and we would then need to define what that inductor current was. Maybe that inductor current is going left to right in a positive manner. Then once we have that defined, we could then set the value of that source voltage based on that initial condition. But otherwise, everything looks the same. The R's come over exactly like they did in the time domain. It's just now we do have some impedance expressions. Now just think of these like generalized resistors for our energy storage devices. Now we have an impedance for our capacitor equaling 1 over SC, and that should look like when you were doing phasor analysis where you were looking at the impedance of the capacitor is 1 over j omega c. Now S generalizes that frequency domain description or phasor manipulation, and likewise instead of j omega L, now we absorb that j omega into S, and S can actually have a real component in addition to that purely imaginary component in j omega. Here, let's just accept that this is what we end up with, and let's talk about then what we can do moving forward. And we've already discussed how we or why those particular voltage sources, what makes them up. Let's now figure out where they actually came from. So those voltage sources are there to account for the initial conditions on the energy storage devices. And what we want to know is how would we, by inspection or by looking at a circuit that somebody gives us, know how to introduce these particular voltage sources. And it looks like the polarity is different in relative to the capacitor's polarity and the inductor's polarity. So let's figure out if there's a way that we can understand how to insert or introduce those voltage sources in response to accounting for the initial conditions on those energy storage devices. Remember what we have for a capacitor. For a capacitor, hopefully you won't forget that you have Eli the Iceman, and for the capacitor you have ice. So I, as a function of time, I sub c of t is now equal to c dv sub c of t dt. That's in the time domain. We can actually Laplace transform that differential relationship between the capacitor's current and the capacitor's voltage, and that's actually what gives us this memory or this dynamic behavior in the circuit. Now if we Laplace transform the current, we'll just call that capital I sub c of s. We then have c times the Laplace transform of the derivative of v sub c. And this is now why it's important to understand some of these Laplace transform properties. The Laplace transform of a derivative is s times the Laplace transform of the voltage minus the initial condition on that particular voltage, which we indicate then as v sub c of 0 minus. If we distribute that capacitor value through the two terms on the right-hand side, then we have SC that scales v sub c of s minus c v sub c of 0 minus. And if we're dealing with voltage sources, then we probably want to isolate or solve for the capacitor voltage and write that in terms of the capacitor current and the initial condition. In other words, let's divide all the terms by what's scaling capital V sub c of s, which is SC, and isolate V sub c of s on one side of the equation by itself. So if we divide both sides through by sc, and if we add c, V sub c of 0 minus to both sides before dividing by sc, then we end up with capital V sub c of s is 1 over sc times I sub c of s plus, and now we have c, V sub c of 0 minus divided by sc. So in fact, those c's cancel, and we have V sub c of 0 minus over s that is there due to the initial condition on that capacitor. And we now have a generalized Ohm's law sitting in the first term. This is now our impedance associated with a capacitor. It's now 1 over sc, and this second term is due to the initial condition. And this actually gives us then, this equation gives us our current voltage relationship on a capacitor in the frequency domain. If that's true, then what we can do is we can now try to write in the S domain or in the frequency domain or sketch a circuit, a schematic that encapsulates this particular expression. So we have a capacitor with an impedance of 1 over sc. We have a current, and now we need to make sure that the current and voltage that we indicate on this schematic is consistent with our time domain expression. And did we write that? Maybe we didn't write that, but our time domain expression up here would be plus V sub c of t minus I sub c of t. So we're using the passive sign convention. The current in the way that we've indicated positive is flowing into the positive terminal of our voltage, and here is our capacitor value C. Here is our time domain current voltage relationship on our capacitor. Now what we want to do is sketch something similar in the frequency domain. And now we see that not only do we have an impedance with an impedance value of 1 over sc, but we also have an additional term, which is actually a source. And now we have to figure out how do we introduce the sign or the polarity on that source. The value of that source will be V sub c of 0 minus. And what we want to do is make sure that this voltage, which now is not just the voltage across the impedance, but it's the voltage that incorporates not only the drop from the impedance, but also the drop from the initial condition. Here is our capacitor's voltage, and if we apply now KVL, let's say that we start here at this negative value of our capacitor's voltage expression, and then go this way, all the way back, and this is now our KVL relationship, maybe through air. Now we have minus V sub c plus 1 over sc I sub c, and then if we say plus, so if we now have this polarity as plus minus, we would have plus V sub c of 0 minus over s, that equaling 0, and in fact that is consistent with the blue equation up above. So this is now the polarity labeling that we need to incorporate in our voltage source that accounts for initial conditions when we put this capacitor in the S domain circuit, equivalent circuit. Let's look at some of the other parameters that we have in common in our particular class, which are R's and L's. The resistor now if we Laplace transform the current voltage relationship on the resistor, we have V sub R of S is equal to R I sub R of S. And I think it's clear that there's no S's associated with that impedance. Here is our impedance in the frequency domain, and actually we don't have to worry about introducing any sources. There's no frequency variable S that scales the R because the resistors have this direct connection in the time domain, or this linear or algebraic relationship between current and voltage. That algebraic relationship carries over directly into the frequency domain. Resistors then carry over into the S domain unaltered, and we don't have to worry about those. We just put those in the circuit in the S domain exactly like they would have appeared in the time domain circuit. And you can see that is the case here. In our S domain circuit, you can see R1 is horizontal in the first mesh, R sub 2 is vertical in the second mesh, and that's consistent with what they looked like, in our initial time domain circuit. Now let's look at what we have relative to inductors. And inductors, hopefully now you're already cued in on what we can use. You can always use Eli the Iceman to help you, so that now we know the time domain relationship between the current and voltage of an inductor is V is equal to L di sub L dt. If we now, like we did with the capacitor, take this into the S domain, or Laplace transform that differential relationship in the time domain to get us into the frequency domain, we now have V sub L of S on the left is equal to L, which now scales S I sub L of S minus I sub L of 0 minus, and that's now our relationship in the S domain that relates the voltage and current of an inductor. And again, if we distribute the inductor value through both terms on the right, we see that we have SL times I sub L of S minus L I sub L of 0 minus. And again, what we can see, or we can identify then, that our impedance in the S domain for an inductor is now going to be given by the product of S, the complex frequency variable, times the inductor value L, and then we have an initial condition term that is present because of this differential relationship between current and voltage in the time domain. Let's now duplicate what we did for the capacitor. Here's our time domain relationship on the current and voltage of an inductor. And again, that's just Eli, so we have V is equal to L di dt. Now what we want to do is have this particular equation, which I can go ahead and just say now V sub L of S, so that I don't have to be quite so difficult with my highlighting. Now I want to realize this in a circuit diagram. And to do that, I can now do what I did like I did with the capacitor. I have an impedance associated with my inductor, and I have a voltage source associated with that inductor. What I need to do now is figure out what the polarity of that voltage source needs to be, so that my equivalent circuit in the S domain will produce that particular expression when I analyze or look at, for example, the relationship between the inductor current I sub L and the inductor voltage V sub L. And remember, this inductor voltage not only has to be associated with the impedance, but it also needs to accommodate the initial condition that might be present on that inductor, and that initial condition is incorporated from the current of that inductor. Again, if we now apply a KVL around this particular path, then doing that, we would see that we have now minus V sub L plus SL times I sub L of S. And now what we want to do is have the sign consistent with what we would have in this equation, which is minus L I sub L of 0 minus equaling 0. And this particular equation now is identical to this equation that we've written from Laplace transforming the differential relationship of our inductors' voltage and current relationship. And to achieve that, then, we needed to have the polarity of minus plus, and the magnitude of that source voltage is now L times I sub L of 0 minus. So that now, anytime somebody needs to introduce this particular inductor or an inductor into a mesh type analysis, then they could introduce their initial condition by incorporating a voltage source with this particular value, L I sub L of 0 minus, and the appropriate polarity, where this minus sign now is where the inductor current enters first as it goes through that particular circuit element. How do we solve then for V sub 2 of S in this particular circuit? And now I've already indicated an I sub 1 of S as a mesh current in the left mesh, an I sub 2 of S as a mesh current in the right mesh. And maybe you can see it's very faint, but my gray labeling on the capacitor's voltage and the inductor voltage are now those particular pieces that not only are associated with the impedance of the capacitor and voltage and inductor, but they also have to incorporate the initial condition terms in order to actually accurately model in the S domain what the voltage across that capacitor or that voltage across the inductor will actually be. It needs to incorporate both terms. So what we want to do now is find I sub 2, which is one of the mesh currents, and determine V sub 2 from I sub 2. And we can determine V sub 2 from I sub 2 just like we did before. V sub 2 is now just going to be R sub 2, I sub 2 of S. Or the main analysis will concern how do I now identify I sub 2 of S. And once you have that in the frequency domain, you can take this into the time domain by inverse Laplace transforming, which is why it's so important to be able to Laplace transform and inverse Laplace transform. Let's look at a matrix formulation of how we could now set the equations up in matrix form to allow us to solve for both I sub 1 and I sub 2, but in this particular example, we'll just focus on solving for I sub 2 of S. In matrix form, because we do not have any dependent sources, we can immediately write down this impedance matrix. This is what I'm calling my impedance matrix Z, and here is my right-hand side, or sort of my, if this is now a generalization of Ohm's law, we have V on the right is equal to Ri. Well, it's a generalization, so now we have Zi. So V is equal to Zi. Our impedance now is a matrix. It's 2 by 2, and how do we fill in this 2 by 2 matrix? In the first row of this matrix expression, this first row should be what we would see if we walked around the first mesh. And in this case, the way to write it by inspection, let me go ahead and get rid of some of the highlighting that I've subsequently or earlier introduced. Now let's say that we're going through and writing our equation here. Well, to do it by inspection, when we're writing the first mesh, the diagonal, well, when we're writing all of the meshes, the diagonal entries in our matrix, and our matrix will be square, it's 2 by 2, will be composed of all of the impedances that touch this particular mesh current. In this case, we have R1 and 1 over SC that touch that first mesh current. And that's now going to be the current, the expression in that 1, 1 entry of our matrix, and that's what's multiplying I sub 1 of S. If we look at that same thought process in the second mesh, now if we put in the diagonal entry, the 2, 2 entry of our impedance matrix Z, we would then put into that term, the 2, 2 entry, all of the impedances that are touched by I sub 2, and that would be this capacitor's impedance, 1 over SC, it would be this inductor's impedance, SL, and it would be this second resistor, R sub 2. The sum of those impedances would then be in the 2, 2 entry of our impedance matrix. The off-diagonal terms are actually going to be the negative of the impedances that are shared by those respective mesh currents. In this case, we only have 2 meshes, so we only have one possible way that they could share. And in this case, if we go back to our circuit, that capacitor is shared by I1 and I2. By shared, I'm meaning that it is going to be seen or touched by I sub 1 and I sub 2. And that means that in this particular expression, in the matrix, our impedance matrix, we would have a minus 1 over SC in both the 1, 2 entry and the 2, 1 entry. The driving or the source terms on the right-hand side are going to be determined by, do they encourage a more positive behavior for I sub 1 in the first case, or do they actually impede that? If they encourage, we will go ahead and put that voltage in with a positive sign. If it actually happened to be a negative voltage, we would say a positive negative voltage, if that makes sense. Hopefully it will. But in this case, we go back to our circuit and we say V sub I, if I made that larger, or if I increased V sub I, would that tend to make I sub 1 bigger, or would it impede I sub 1? And in this case, V sub I, if I increased it, that would increase I sub 1, so I write V sub I with a positive sign. Contrast that with this particular capacitor's initial condition voltage source, and now if I increase that, that's actually going to try to impede an increase in I sub 1, so I would now subtract that particular voltage source in terms of polarity, or in terms of its algebraic sign, in my right-hand side expression in the top row. And that then leads to a positive V sub I of S minus V sub C of 0 minus over S. If we do the same thought process for the second mesh, now is that capacitor's initial condition voltage source, the V sub C of 0 minus over S, if I made that bigger, would that enhance I sub 2? Yes, it would. What about the inductor's voltage source, L I sub L? If I made that bigger positively, then that also would enhance I sub 2. In that case, in the second equation, I now need to introduce V sub C of 0 minus over S plus L I sub L of 0 minus. And that's what we have then to create this matrix formulation, which is really just Zi is equal to V. Then we can use Cramer's rule, which is a ratio of determinants, where if we're solving for I sub 2, in the numerator expression, the vertical lines are just saying the determinant of this 2 by 2 matrix that has polynomial entries in S. But now the second column is just going to be the right-hand side of our Zi equal V equation. The left column is simply the left column in our impedance matrix. And the denominator is another determinant, but that determinant is the entire impedance matrix without having to substitute or replace any of the columns in our original impedance matrix. We just write that down and find its determinant. This would now give us I sub 2 of S if we compute the determinant, and those determinants are, in this case, it's 2 by 2. You would have the product of the diagonals minus the product of the off-diagonal terms. And that would then be the way that you would compute the denominator. The numerator would be computed in the same way. You would take the product of the diagonal entries and subtract the product of the off-diagonals. This is now a way to immediately write down or go into the S domain and solve with algebra. We didn't have to do any kind of differential equations. We simply are now playing with algebraic techniques, but now our algebra involves factors or rational expressions of S, but as long as we keep track of those, we will end up with an I sub 2 that will be a rational expression in S scaled by R sub 2 will now provide us with V sub 2. We can then inverse Laplace transform that V sub 2 of S to obtain little V sub 2 of t. And that is how I would like to then motivate this concept of working in the S domain directly in performing circuit analysis.